Today we will study the concept of an ordinary differential equation. But why we study an ODE? Is there any significance of studying this concept ODE? This is an environment. We are the elements of environment. Trees, animals, human beings, mountain, rivers, sky, these are all elements of an environment. But what is the relationship among these elements? This ODE concept gives an answer, gives a reason of this relationship, the significant relationship. This is an environment, but how we measure the environment? There is change, but how change measures? This is the concept of measuring the rate of changes. Do you know velocity and current, heat and wave, growth of population? There are some examples of changes occurs in the nature. What is velocity? We know that there is a particle at position x, but after some time the position is changed from x1 to x2. It means a natural change we can see, but in this change of positions of any particle x1 to x2, a certain time is required. It means there is a function. We can say that function is y equal to fx, and velocity is the function of time. The same the current. Current is again a variable. We can say that I, but after time t, what is change in the charge? There is the electrical charge. The rate of flow of charge is the current. Simply we can see that dx by dt. We know that x is variable, that is nothing but the displacement. We can say that there is t, small t. This is again the variable, but represented as the function of x of t. Then after time t, the displacement we can see, the displacement from one point to another. The rate of change in the position of that particle is the velocity. But the word is very chaotic, not understandable. The same change, if we express by the equation dx by dt or d by dt for x, we can say that the change in x with respect to time t, that is dx by dt, this is a derivative, is called velocity. The same is the current. Instead of the position x, the displacement x, here again I is the function of t. I is an electric charge. The change, the rate of change in that charge with respect to time t is denoted by di by dt. This is nothing but a current. It means change in the charge with respect to time is nothing but current. This is represented by di by dt. Then we have to understand what is the differential equation. Differential equation is nothing but an equation involved differential coefficients. It means an equation involved variables dependent and independent and derivatives. This is a differential equation. We can see that f is a function x, y is the function of x, and dy by dx is derivative, d2y by dx square is the second order derivative, similar on up to nth order derivative. In general, we can say that dy by dx is a change in y with respect to x. d2y by dx square is the change in dy by dx with respect to x. It means dy by dx is velocity, and change in the velocity is called acceleration. Therefore, we express any equation like dy by dx plus y equal to 2 is a differential equation because it consists derivatives with the variables. Second, or we can also say del z by del x. This is again a differential equation, but this differential equation is a PD. Why PD? Because del by del x, there are three variables. It means z is the function of x and y. Next, we will study what is the difference between ODE and PD. ODE, very simple definition. If there is only one independent variable, that is y equal to fx. X is the only variable. Therefore, if we study the change in the function y equal to fx, then we require ODE. Therefore, we can say that xy dy by dx d2y by dx square up to nth order derivatives. Only, this is important, that only x is the independent variable. If there is only one independent variable, it means this is an ODE. Similar on, this is the generalization of ODE, that is the PD. The only one thing to be noticed here, number of dependent variables are more than one. It means 2 or 3 or 4 or n. We can say that z equal to fxy, z is the dependent variable and xy are the independent variables. It means there are two independent variables, x and y. Then the change exists as del z by del x, del 2z by del x square, and so on. Application of DE. We know that there is the theoretical aspect of differential equation. Already we studied DE as measuring the nature, measuring the environment, measuring the changes, measuring the rate of changes. That is heat, wave, current, population growth, structure of compounds, whatever we need the model of the nature or environment or interrelationship between the variables is the applications. We can model the physical system through D. Very simple basic concept we need to remember. These are the key concept. Order. How many times we derive, how many times change occurs. This is represented by the order. We can see here d2y by dx square, the maximum derivative is 2. dy by dx, this is the derivative single time. It means what is the maximum time derivative, maximum coefficients, that is d2y by dx square. It means what is the maximum derivative, that is called order. Here we can see that d2y by dx square is the maximum but not dy by dx. Therefore, its order is 2. Similar, the extension of order, which we can see that d2y by dx square, the index of this term is 4, but we can say that dy by dx, the power of dy by dx is 5. Now, which one will be the degree, 4 or 5? Definitely 5 is greater than 4, but 4 is the power of maximum order derivative. Therefore, degree is 4 but not 5. Then we can say that the power of highest order derivation is, we can see, 4 is the degree. Thus, this equation is called fourth degree equation. In the concept of degree and order, the generalization we see here as the linear differential equation. Linear is nothing but the degree 1. An equation of degree 1 is called linear differential equation. This is an equation. We can see that dny by dxn, this is the nth order derivative, dn minus 1 y by dx n minus 1, this is order n minus 1. We can see that there is no power occurs here. Therefore, the power is here, but that is 1. Therefore, this is the first degree equation or linear differential equation. Very simple, which is not linear. It means simply we say that if the degree is more than 1, that is 2, 3, 4 and so on, then the differential equation is not called linear but non-linear. We can see that d2y by dx square, this is the second degree equation, this is the non-linear equation, and we can see in the second equation d2y by dx square again multiplied by dy by dx. It means we cannot say the power of this term will be 1. Therefore, this is also a non-linear differential equation. The flow of d, it means what are the characteristics, what are the applications. It is depend on formation and solution. In nature, there are only variables, but there are hidden functions. If we solve some problem, then first we need to define what is the problem. Therefore, formation lies with problem and solution simply it solving. Very simple, we have an equation f x y z equal to 0, but this is not a differential equation because it does not consist derivatives. Only these are x, y variables and c is the constant. There is no derivatives. It means this is not a differential equation. It means we can convert, we can form this simple equation into a differential equation. But how? Very simple, by eliminating c. C means arbitrary constant. If we eliminated c, then instead of c we put dy by dx, it means derivative. Then we can say that f xy dy by dx is a differential equation and ODE because c is not here. Instead of c there is dy by dx. Now how we solve the problem? We can see that f xy dy by dx equal to 0 is an ODE. But how we solve? What is the meaning of solution? Solution lies with the value of y, because y is represented as the two type. First, y is the simply function of x, and secondly dy by dx. It means the change is defined on y and represented by the derivative dy by dx. Then what is y? Independently, what is y? The challenge of finding y is the method of solving differential equation. This is defined by, or in number line, x is the minus infinite to infinite. In the number line, we can find any particular value which is definitely continuous as well as differentiable. But how the points occur in that real line, next we will discuss. Solution of equation in separable form. We know that to find the value of x is the solution of any differential equation. Here we can see that dy by dx equal to fxy. This is nothing but an ODE. But we can see that dy by dx can be represented into right hand side, that is the two term gx and hy. Means we know that if derivative is integrated, then it becomes just the variable. Then we can integrate easily. If we separated x term into one side and y term into another side, there is dy and there is dx. We can integrate dy and dx separately. See here, dy upon hy, just a function of y. Another side, gx, is nothing but a function of x only. Simply we integrate both sides, and another function we have ay equal to bx with the arbitrary constant c. If this is not possible to separate the variable like this, then there exists some cases we will discuss further slide. This is the very simple. See that f ax plus by plus c. It is definitely a function, but not able to write this function into the separation of variable. We can substitute some term, that is ax plus by equal to v, then it can be formed into the separable form. This is the function of the type reducible into separable form. Very simply we substitute x plus by equal to t. Then after derive, we can substitute another function that will be definitely a separable function of first kind. Then we can solve as earlier. Equation reducible into separable form. This is another example of reducible into separable form. Again here a upon b and a upon l, b upon n. Simply we substitute these variables into the term a upon l equal to b upon n. Next case may be a upon l does not equal to b upon n. We can simply substitute these term and reduce into separable form, and again by applying the separable method we have the solution. This is the exact first order ordinary differential equation. Exact means a condition. We can see that mxy, if there is not exact differential equation, then what? For this we have an integrating factor. But how we obtain the integrating factor? By this integrating factor we can reduce non-exact differential equation into differential equation. This is the concept of integrating factor. We can see here with the condition. First condition is del m by del y minus del n by del x divided by n is only function of x. Then simply the integrating factor will be e raised to fx dx. We multiply this integrating factor into the original equation, then we have the solution. This is another case. The same left hand side, only in the denominator there is m, but in the right hand side there exists only function of y. It means the integrating factor will be e raised to gy dy. By multiplying this integrating factor into the original differential equation, and we have the exact differential equation. The another case is again for non-exact homogeneous differential equation of degree n. This is a critical and more advanced than earlier two. Here mx plus ny does not equal to 0, then it may be 1 upon mx plus ny is the integrating factor. Maybe mx plus ny equal to 0. Then there are the cases either 1 upon xy or 1 upon x square or 1 upon y square is the integrating factor. If we multiply this integrating factor into a differential equation, then it becomes an exact differential equation. Now a wonderful topic we have, that is the linear first order differential equation. This is again discovered by Newton and Leibniz, who also credited to discover the calculus. Differential equation is the branch of calculus. Differential equation is an application of calculus. Newton and Leibniz applied this differential equation for modeling the physical system in 17th century. Euler had the maximum number of citations. Maximum applications considered Euler algorithms, Euler's problem, and various aspects of Euler's method. All is based on differential equations and its applications. We can say that the linear first order ordinary differential equation by Leibniz, linear differential equation. How we identify the linear differential equation? Simply by fx dy by dx plus gxy equal to hx. But here fx is the coefficient. Now we divide this equation by fx. Then we have dy by dx plus pxy equal to rx. We are interested on the coefficient of y and the right hand side term rx. This is very important for obtaining the integrating factor. Very simple, the coefficient of y, that is px, and it becomes e raised to px dx, which is an integrating factor. Linear order of ordinary differential equation of order n. That is the first order, previously we have studied, but this first order is generalized into nth order linear ordinary differential equation. We can see that dny by dxn, but there is the coefficient a0x, either variable coefficient or constant coefficient. We can write this coefficient in the term of f dy equal to rx. D is the differential operator. In the term of d, the equation is very attractive and simply defined as the polynomial form. Therefore, we can write the whole equation in the term of f dy equal to rx. Fd is the polynomial containing the derivatives, and rx is the right hand side, which is also a polynomial. The solution, very simple, we can define its solution. There are the points yx0 for constant 1, y dash x0 equal to c2, and similar on yn minus 1 for cn. If there is nth order linear ordinary differential equation, it means n arbitrary constant. Which one? c1, c2, c3, c4 and so on cn. If third order ordinary differential equation, it means there are 3 arbitrary constant C1, C2 and C3. If 4, then 4 arbitrary constant, 5 means 5 arbitrary constant, and always x0 belongs to I. Solution of second order linear differential equation, and it extends into nth order linear differential equation. But how we start to solve this second order linear differential equation? Very simply, we can see here a is the constant coefficient d2y by dx square plus b dy by dx plus cy equal to rx. If we apply differential operator capital D, then it becomes ad square plus bd plus c, and all the terms is defined by the function of operator d, and fd is a polynomial, and this polynomial has definitely the roots. Therefore, the nature of roots may be real and distinct, real and equal, and complex roots. It depends on the nature of roots. Always there is two types, homogeneous and non-homogeneous. If there is non-homogeneous differential equation, then there exists pi, particular integral. And if there is homogeneous, then only we obtain fd, the roots of fd. It refers by cf, complementary function. Why the pi exists? Because Rx is 0. Then fd y equal to 1 upon fd. Fd does not define because in right hand side there is 0. Therefore, does not exist pi. If Rx does not equal to 0, then the solution carried complementary function and particular integral both. Then this is the solution y equal to cf plus pi.